We're not having lab tomorrow, but remember next week to dress properly for lab because it's getting warm and it's easy to forget to wear proper shoes and everything. Everybody had a good weekend? Everybody got you sunburned or anything in the first nice sun? But
I went to Six Flags.
oh, fun. Yeah.
And last Saturday, my friend's sister's company have some event there, so we bought ticket discounted.
Nice.
Price.
Good. Did you go on all the rides?
Oh, not really, because we have another plan. So.
Okay. No puking or anything.
No.
All right. So with these equations, you don't need to really know what kind they are to fill them in. Then you can label them afterwards. But we can just add up the numbers as we've done in class and should get the correct particles. So you've got 84 over on that side, then this side's going to be 82 and 2. 210 means this one's going to be 206. Then you look up at the periodic table and you see that that is lead. Okay. What kind of decay is that? That's alpha decay, right? Because this is an alpha particle. All right, next one, we have to go the other way here. So 92 and minus 1 is going to be 91. And then 254 on top. And that is protactinium, Pa. What kind of decay is that? All right, that's beta decay because of the beta particle. And then the last one is a bigger reaction. Might help to first say what kind of a reaction this is. It's not actually. Yeah, there's 5 choices here. So we've got alpha, beta, gamma, nuclear fission, or nuclear fusion. What is this one?
Something about sun?
Yeah, this one's fission because it's breaking apart. So that's nuclear fission. The uranium is breaking apart when bombarded with a neutron. So we have to add all this up. 235 plus 1 on the left is 236 total. On the right, we've got 90 plus 3 for the 3 neutrons, which is 93. So 93 to 236 is 43. Or whoops, 143. And then the bottom number is going to be 92, has to equal 92. So 38 plus what is 92? That would be 54. I believe that's, isn't it? Any questions about that one? Good. All right. Now we'll look at some half-life. The half-life is 4.5 days, 4.5 days. That means it breaks in half every 4.5 days. If it starts, or I'm sorry, rather than starting at a certain amount, we say after 27 days, it's at 1 microcurie. So that means at the end of 27 days is 1 microcurie. What did it start as? What was the initial activity at the beginning? So how many half-lives is 27 days? It's 6 half-lives? Because, yeah, 2 is, well, it's 4.5, then 9, and yeah, so 6 half-lives. So we have to go 6 half-lives. So 1, 2, 3, 4, 5, we need one more. 1, 2, 3, 4, 5, 6 half-lives. So after 6 half-lives, we've got 1. So then we count back to see what we started at. So that's 2, 4, 8, 16, 32, 64. If you cut 64 in half 6 times, you get 1. So that means that the initial activity was 64 microcuries. Did anybody do it the opposite way? Start at 1 and then go from there? No? Good. Okay. All right, and then we can convert that and do the same problem in microbecquerels. where we just use this conversion factor that's given here, 64 microcuries, and we're going to convert microcuries to microbecquerels. So that's 3.7 times 10 to the 10th. Let's see. 64 times 3.7 is 236.8. Or, since we usually don't do scientific notation that way, you would call that 2.368 times 10 to the 12. Either way is fine. Any questions about that? All right, then let's move on. Okay, so our last topic of the semester. We're going to talk a little bit about organic chemistry. Some of you might go on to take organic chemistry. Chem 201 is the one semester organic class here. So if you only need one semester of organic chemistry for whatever you're going into, you can take that one. There's also a 2-semester sequence, but you really need to take the general chemistry sequence before that one. At any rate, it's an important part of biological systems and things like that. So it's important that we get at least a basis for how these molecules look and how to draw them and what they're like. So that's what we're going to be working on for the next couple weeks. All right, so organic chemistry, anybody know how we define it? What is organic chemistry? How is it different from the other stuff we've been doing? You know? Have you heard this term before, organic chemistry? Something you're familiar with a little bit? Yeah. Organic chemistry, the name organic comes from life. Organic meaning coming from life. And it comes from kind of an old idea that there's scientists used to think long time ago that there was an important difference between things that were made from living things and things that were made from non-living things. So you had organic substances that were made by living things, and you had inorganic substances that were minerals that were made by non-living things. Now we know that's not really a good distinction, that we can synthetically make the same molecules that are made biologically, and biology depends on a lot of inorganic mineral type stuff too, so it's not really a good distinction. So now we use more kind of an arbitrary chemical distinction to say that we're going to focus on molecules made of primarily carbon. It's going to be the most important part of organic chemistry. And then also nitrogen, hydrogen, oxygen, and some others. But the main part about organic chemistry is that we're focusing on the chemistry of carbon and how some of these other things interact with carbon. There are various reasons why that's important. One is that it's pretty predictable chemistry. So we know a lot about how these things are going to happen. We know carbon's going to make 4 bonds, for instance, pretty much all the time. And these are molecules that are really important to life. So organic chemists might do things like develop new drugs or study the way that things interact with living systems, things like that. All right, so first we need to review a little bit about the structure of carbon. We know, first of all, that carbon has how many valence electrons? 4 valence electrons. And that means that it has kind of 4 spaces because it wants 8. So 4 spaces where it would like other electrons to be. And because of that, it can make some bonds. It makes covalent bonds. For instance, it could bond with 4 hydrogen atoms. And this wouldn't really be a true chemical reaction, but we can think about it this way. 1 carbon atom with 4 hydrogen atoms could connect to make a molecule that looks like this. So each hydrogen and each carbon are sharing, or each hydrogen is sharing 2 electrons with the carbon. And that way their valence shells are all filled. And we might draw that with lines instead of dots, like this. But there is a little bit of a problem drawing in this way, drawing methane in this way. And this molecule is called methane, by the way. Here. Methane. The problem is that the real methane molecule is not flat, and the bond angles are not at 90 degrees. So if we think of this angle right here, that looks like 90-degree angle. But in a real methane molecule, it's not. So this is maybe not the best way to express this structure. A better way is to think about what this thing would really look like in space and see if we can draw it that way. So I could have brought some models down, but I decided to just do it on the computer today. I've got a methane model on the computer here. This is what the methane molecule looks like. Now you can see we can kind of put it in a way that makes it look like well, that's all right. That's as close as we can get it. We can put it in a way that kind of makes it look like it has those 90-degree bond angles. But when we turn it around, you can see that that's not really the case. That it's actually a very different kind of shape. Does anybody know what this shape is called? Have you seen anything like this before? The way you can think about it is think about it being inside of a cube. If it's inside of a cube, in fact, we can draw this here. No, it's not going to work here. Let me copy it over to the other program, then we can look at it. Just going to take a piece of this and put it over here. All right. So we can imagine that gray ball, that carbon atom, in the middle of the cube. That's our carbon. And then the hydrogens on the corners of the cube, kind of alternating corners across the diagonal. So let's see if I can draw this here. So something like, if we connect those corners like this, if you imagine those corners connected like that, that is a specific shape called a tetrahedron. And so this type of geometry is called tetrahedral. And this is a regular solid, meaning everything is the same length. It's a 4-sided solid. You can think of it like a 4-sided pyramid. But everything is the same length, all the sides are the same, all the angles are the same. Any idea why this molecule would adopt this shape instead of just being flat, where it would be easier to draw? What do you think is an advantage of this shape? Ideas? The advantage of this shape is that the hydrogen atoms can be a little bit further apart. So the bond angle between these two, remember the angle that we drew up here when it's flat was 90 degrees. The bond angle right here between those two is 109.5 degrees. So bigger than 90. And that means that the electron clouds in a tetrahedron are going to be a little bit further apart from each other than in a T-shaped or a cross-shaped molecule. That means that that's going to be a little bit more stable because we know electrons repel each other. So if we can keep those electrons a little bit further away from each other, that makes for a little bit more stable molecule. Okay, so that's the geometry here. Now we want to make a way to draw this that expresses this particular geometry. And the way we do that is called dash wedge notation. So we'll put the carbon in the middle, and we think about what's really happening in the structure. The one going up, we just draw as normal. The one going off to the side here, we draw as normal. But then the other two, we have to express the fact that those two are actually in line with each other. One is going backwards into the screen, and the other one is like it's coming out at us. So we use two different symbols to show that. The one that's going back is written on a dash like this. And the one that's coming out at us is written on a wedge. So that makes the other two directly in the plane of the screen. The ones on the normal straight bonds are directly in the plane of the screen. The wedge is coming out at you. The dash is going back. I should note that the dash is coming out toward us, just like this one over here, and the wedge going back away from us, which is like this one. So you'll see that type of notation sometimes in these organic structures, talking about the geometry and where these things are. Okay. So now that we've kind of set that up, we're also going to ignore this sometimes because sometimes it's just easier to write things in a straight line and make it all look nice and neat. What I want you to do is to realize in your brain that that's not really the geometry of that structure. That if we draw things in a straight line, we're not really saying this is what it looks like. This is just a way that we're expressing it right now. So let's do that. What we're going to do in this chapter, and then a couple I guess it's a chapter and a half or so, is we're going to look at some different categories of molecules. We're going to talk about how to draw them and then also how to name them. And first chapter that we're going to look at, or the first classification we're going to look at, are some molecules called alkanes. Alkanes aren't super important from a reactivity standpoint. They don't do a lot of interesting reactions, but they're important from a fuel standpoint. They burn. And that's pretty much the only thing they do. And what's important about them is that they burn. It's a little oversimplification, but that's all right. Alkanes are defined as molecules made of only carbon and hydrogen with only single bonds. So we're going to look later at some alkenes, alkynes, some other molecules that have double and triple bonds. Those are going to be in different categories. The alkanes are only single bonds. We're going to build this up from simplest to, or smallest to largest, look at some structures, look at some names, and then kind of branch off from there. So we'll set up a table here. The molecular formula of the alkane, the structure, that is, what does it look like? Give ourselves a little more room for that one. Name, and then what we call the condensed structure. I'll tell you what that is when we get to it. It's just a way of writing it. It's a little bit easier and quicker as these things start to get a little bit bigger. All right. So we'll start with our simplest, smallest alkane of all, which we've already talked a little bit about, and it's methane. CH4. And its structure, as we know, is this one up here. But we can also write it, for our purposes right now, as just like this. So we're going to stick with the regular 90-degree type structures just to make things easier right now. The name of that is methane. And in a condensed structure, we're going to condense the hydrogens onto the carbons that they are attached to. So for methane, that's pretty simple. There's only one carbon, so the condensed structure is just CH4. As we get bigger, you'll see there starts to be a difference between the formula and the condensed structure. All right, so let's do that. Our next one is going to be C2H6 with a structure where two carbons are attached and then surrounded by hydrogens. Notice again that we have the wrong geometry here, that really it should be these angled bonds, but just because that's not what we're focused on right now, we're going to use these as a shorthand. The name of this one is ethane, so only one letter different. Just drop that M, you've got ethane. And the condensed structure looks like this. So we're going to take those two carbons and collapse their hydrogens onto them, but write them next to each other. The reason for that is it gives us a little bit more information than just the molecular formula. The molecular formula only really tells you how many of each kind of atom there are. The condensed structure lets you know a little bit about how they're connected. And as this gets bigger, you'll see how this can help us. Next member of the list, and this is the last one that we'll do together here, C3H8. It's called propane. And now I want you to try to draw the structure. It follows the same pattern. Carbon has to have 4 bonds. Hydrogen has to have 1. There's really only one way to write it. So see what you can do. You can draw the structure. right. Sort of see a couple pretty good. Well, hopefully you got something like this. Yeah. And what do you think its condensed structure is going to look like? Yep, you got it. CH3, CH2, CH3.
So we have 3H one side, 3H second side, and this is between two.
Right, and the 2 in the middle one. Everybody see where that comes from? Okay. The fourth member of the series is called butane. See if you can fill in all the rest of the information. And I would recommend you leave the formula till last. So do the structure, do the condensed structure, and then calculate the formula. But I think you can get all of it. All right, so you got probably something like that for a structure. And then your condensed structure is going to be CH3, CH2, CH2, CH3. Yeah? And actually, we can abbreviate this even a little bit further. We could also call it, if we want, CH3, and then 2 CH2s, and then CH3. That can become useful when it gets really big, like 10 or more carbons. But even this, you probably realize when you were writing, it's a lot easier to write this than to write this. So the condensed structure can save us some time. It's also a lot easier to type this, if you need to type something, than to try to put this into a document. And then the formula becomes C4H10. You'll notice, I don't know if anybody noticed, but there's a pattern here. All alkanes have a formula of whatever the number of C is, the number of hydrogens is twice that plus 2. And we can think of that as being each carbon gets 2 hydrogens, but then the ends get an extra one. So any way you draw an alkane, it's always going to have that same kind of a formula. Now, these go up. There are more, of course, members of this group. Some of these you may have heard of or seen. Methane and ethane are the main components in natural gas, which is this stuff that we burn in our burners, that you burn in your furnace at home, all of that. Propane is a easily liquefied gas, so you can pressurize it a little bit and it becomes a liquid. So that's why they use liquid propane like tanks for the grill, or if you live outside of the city, you might have a giant propane tank that supplies all of your power because it's a little relatively easy to transport compared to natural gas. Butane is even more easily liquefied, so we see that in things like lighters, where it can be liquid in the lighter, and then as soon as you just very lightly pressurize, and then as soon as you open it up, it turns to a gas. there's a little table we'll grab from the book here. So you can kind of see all the stuff that we've been doing. Here's a nice table that shows the first 10 of the alkanes. We're going to mostly deal with, well, I'm going to put all these on here just in case we need them for today. But according to the objectives on Blackboard, you need to know the first 6. So no methane, ethane, propane, butane, pentane, and hexane. And then if you need the other ones, I'll give them to you on the exam. Something interesting starts happening when we get above 4. And that is that you can draw the same structure, or you can draw 2 different structures with the same formula. So let's look at pentane, which is C5H12. Actually, 3 different ways you can draw pentane. There's 2 different ways you can draw butane. So we can draw 3 different structures that all have the same formula, that are all C5H12. And the easiest way to do this, I think, is to focus just on the carbons. So one version is just straight across, the ones that we've been doing. And then we can fill those in with the hydrogens. But I'm just going to leave those there for now. Another way we could write this is to break off one of those carbons from the end and stick it somewhere in the middle, like this. And then there's a third way that looks like this. We could break a second one off and put it on the same carbon with that first one. Those are all different molecules. They have different properties, different boiling points, different melting points, maybe different ways they react in some situations, different crystal structures. So they're not the same. They're not the same. And there's a word for these structures that are not the same. And that word is isomer. Isomers are molecules the same formula, that same C whatever, H whatever, but different connectivity, meaning it's connected in a different way. The carbons are attached, or the atoms are attached to each other in a different way. For completeness here, we'll fill in the rest of the hydrogens. You can see why the condensed structures start to get a little bit easier to deal with here. We could draw these a lot faster that way. So one thing that you should be able to do is to find isomers of different structures and see if they are indeed isomers or not. And one common mistake that I see in these kinds of things is somebody drawing something like this as an isomer and leaving the hydrogens aside for now. Why is that not an isomer? Is what? What do you mean?
The last part.
Yeah.
It's connected to the before that.
So if this is not an isomer, what is it then? You're right, it's not an isomer. So what is it?
We mentioned it before, yeah. Alkane.
Well, the isomers are all alkanes, yes. The reason this one is not is because this one is the same as this first one. Single bonds can rotate, and as we talked about, these aren't even the real structures. They really should be kind of zigzagged. So to just kind of bend one side down is not changing the structure at all, because it can always, you can draw this however you want. We're drawing whatever angles we want here. These are a little bit different. You can't make this one from this one just by twisting it around. You have to actually break this off and then attach it onto the side here. So that's very different. So isomers have to not be the same. That's an important aspect of them. And one thing that's going to help us with that is when we start talking about naming them. We're not going to get to that today probably. But one thing you can look for is a continuous carbon chain. So you look at this one and you can count 1, 2, 3, 4, 5 carbons all connected in a row without picking up your pencil. This one you can do the same. 1, 2, 3, 4, 5. So that's a clue that those might actually be the same. This one, the longest chain you can get is 1, 2, 3, 4, or 1, 2, 3, 4. But you can't get that fifth one without picking it up and drawing somewhere else. Here's just 3. 1, 2, 3, or 1, 2, 3, or 1, 2, 3. However you want to count that, you can't get more than 3 carbons in a row without picking up your pencil and then going to the other ones. And that tells you that those are all different. So now I want you to do this. I want you to find isomers of hexane, which is C6H14. And we're going to work together on this. So I want everybody to draw, let's say, 2 or 3 structures. There's several of these here. So think about it a little bit yourself. Draw a couple. And then group yourself into groups of 3 or 4 or something, whatever you can reach. Look at what each other have drawn. And let's see if we as a class can actually get all 6. So when you think you've got one, when you talk to some other people about it, 1 or 2, draw it up on one of these boards somewhere. And we'll see if we can get all of them. I believe there are 5. That's some good ones. Start putting them on the board so we can get all of them accounted for.
Yes, we could.
Yeah, we need 6 carbons.
I'm sorry, I have a question. I'm not sure about it. Can I arrange the reaction this way?
Sure.
Yeah.
If you do all of them, but you may have. This is actually the same as this.
CC, and here CCC, and here 2 chain, 4
Right.
chain. Here 4 chain, and here 1, 2, 3 chain.
Yeah.
Mhm. Okay. Do we need to draw that?
Well, let's see what's up there first, and then draw any that you have that are not already up there. We'll see if we can get all of them.
Did you say there were 5 or 6?
6.
Yeah.
All right, let's put them up and we'll see. I don't actually know. I don't have them here on my notes, so we'll see.
What?
Yeah, go ahead if you've got a different one. Let's get a few different ones up there. Even if there's more than whatever number I said, it can be helpful to look at some different ones and see if they're actually the same or not. There might be 7, 5, 6, 7. I don't know how many of them there are total. Okay. If anybody else has some that look different, please go put them up with the others so we can compare. Any other ones? So let's see, there's like 8 up there. I think 5 is the right number. So that means there's going to be some redundancy. Does anybody see 2 up there that they think are maybe not different? Good one.
This one is
This one?
yeah.
Yeah.
First one.
The first one?
Seems like it's the first one.
Yeah, so one way we can look at this is by counting up the carbons in that line and then seeing what other things are attached. So we might say 1, 2, 3, 4, 5, 6. And then this one over here has that same kind of line there.
But if we will move it in the middle, it should be okay.
Yeah, so if we move something over, that might be now a different one. So let's look at those. So those 2 are the same. So we'll put a parentheses around that one because it's the same as the first one. What else? We still got way too many up here. So what other ones might be the same? The ones with 5. So this one and this one. Let's take a look at it. So we go 1, 2, 3, 4, 5, and then the 6th carbon down there. And then 1, 2, 3. So yes, those both have 5 carbon chains, but they're different because in this one, the carbon is on the 4th carbon, and this one, the extra one is on the 3rd carbon. So we can see how that's a little bit different. And even if we number them starting on the right instead of the left, we would still get the same thing. So those are actually different. This one? Yeah. So this one, they look pretty different, so that's how this can be confusing. But this one, and this one are all the same. Because in all cases, they have 4, 1, 2, 3, 4, 4 connected carbons with another carbon coming off of number 3 and coming off of number 2. You see that? So 1, 2, 3, 4, coming off of number 2, coming off of number 3. And then what was this, the other one, this one right here. So then we've got coming off of number 2, coming off of number 3. So those 3 are all the same. But good job, you found all 5 of the different isomers. So these are all 5 different ones. Now when we write those out, it's really not appropriate to abbreviate them with just the carbons like that. So we should really add the hydrogens in. And if we don't want to draw them all out, we can do it in a condensed type structure. So if we want to catalog these isomers here, we could say, do like this. Adding those hydrogens can also help you to pick out which ones are isomers and which ones are the same, because the groupings of hydrogens could be a little bit different. So you could think about things like how many CH3s are there versus CH2s. This structure is the only one that has just a carbon with no hydrogens on it in the middle there, because it's connected to 4 other carbons. And when we get into naming on Thursday, that will be another way to distinguish isomers from one another, if they have the same name or not. All right. Those are our 5 isomers of hexane. Well, on Thursday, since they can't all be called hexane, they'll all have different names, and we'll talk about how we determine those names. It's a lot like our other naming rules. We'll have a set of rules that you have to follow so that compounds always get the correct name that is different and unique compared to others. So I'm sure you're excited about that on Thursday. That'd be super fun. So no lab tomorrow, but I will see you Thursday, and grab your stuff on the way out up here. Thanks.